Okay, so let's go through a little bit about circuits. I'm on the PhET Circuit website. I'm going to do a lab. And first, I'm just going to make a simple circuit with a wire and a single resistor. And we tend to just use resistors instead of light bulbs, but you can use a light bulb. You can change the resistance of it. Um, and so let's change this to, I don't know, let's change it to 12 volt. We've got a 12 volt battery. We've got a 10 ohm resistor. We've got current flowing around because the circuit is closed. If I break this, the circuit is open and nothing can flow. So first, let's just take a look at how we draw that. If you come down over here and you click this button, they will actually change it to how we draw circuit diagrams. Now, they actually have something wrong here compared to what we do for regents. If you take a look at the reference table, we see all these circuit symbols. They drew a cell. If the Regents asks you to draw a battery, you need to make sure you use the symbol for a battery on the Regents reference table. Okay, so I'm going to take this and I'm going to draw it on my board over here. So I'm going to switch so that you can see. We've got a battery. They're not going to care which way you draw it, but what's really important is that for every long I have a short, because those are representing positive and negative terminals. So a battery is really just multiple cells together. That's what a battery is. And then I have a resistor, and that's it. That's everything I have right now. So let's go back and look at this. Let's look at it again like this. Let's say I wanted to add an ammeter or a voltmeter. When I add a voltmeter measures the voltage, what we call voltage drop across the resistor. In other words, how much voltage is being lost. So this is a 12 volt battery. What that means is that this charge, this single charge of Coulomb, I'm pretending that is a Coulomb of charge, is carrying 12 joules of energy. Well, on this side compared to this side, it has 12 more joules is really what's happening. And as the charge goes around the circuit, it has to lose all 12 joules. That's just the rule. To get from this side to this side, all 12 joules have to be lost. So if I measure this, don't worry about the negatives and positives. It just means you have it. It just means you might have switched the terminals you're on. So don't worry about the negative sign. Just think about the absolute value. So the voltage being measured is really the voltage difference on either side of this terminal. That's really what it is. So on this side compared to this side, there is a 12 joule per Coulomb difference, okay? So as this charge goes all the way around, it loses 12 joules. Same thing over here. On this side of this resistor compared to this side, there is a 12 volt difference. That means this resistor uses all 12 volts. It gets to keep all 12 volts. Let's take a look at how I draw a voltmeter. If I want to measure the voltage on this resistor, I will put a voltmeter in parallel with my resistor. For voltmeters, I have to have the choice to go through the voltmeter or the resistor. Let's say I wanted to put an ammeter in because I wanted to measure the current. If I want to measure the current that's through that resistor, what I should do is right before or right after the resistor, I should put my ammeter in. The important thing with an ammeter is since I'm measuring current, I need to make sure the current has to flow through it. So I'm measuring the current through that resistor. And so how do I draw that if I was going to draw it for a Regents exam? Just like this, A. And really I could put that ammeter anywhere in this circuit because as long as it's part of this circuit, it has to flow through it. Any charge that flows right here has to flow here, has to flow here. Has to flow here, has to flow here, has to flow here, has to flow here. Here it has a choice. It gets to go through the resistor or through the voltmeter. And we like that because as it goes through the voltmeter, it tells us how much energy it has. That's why we put the voltmeter in parallel. Okay, let's just look at it quick. I wanted to calculate something. Well, we know the voltage of this battery and we know the resistance of this resistor. So let's go back and take a look at it, right? We said this was a 10 ohm resistor, and we said that the voltage in the battery was 12 volts. So I come back and I do a little calculation and I say, okay, maybe I want to know the current. Current is going to be voltage divided by resistance. This is just on your reference table, you have this equation. I'm rearranging it. So I take my 12 volts and I divide by 10 ohms and I get 1.2 volts per ohm. Totally acceptable unit. You're also allowed to go, oh, you know what? I know that current is measured in amps, so that's the same thing as 1.2 amps. Okay, that's a simple circuit. Let's look at the next type of circuit we might have. I'm just going to completely refresh this. Do it again. There's probably a clear button somewhere, but oh, there it is. It's right there. I can't see it because on my screen there's a little video thing in the corner. So let's put a battery in. Sure, actually let's use nice numbers. I like 12. We're going to keep it a 12 volt battery. Let's put a wire in. And this time, let's have two resistors. So I'm going to have one resistor here. And I'm going to have another resistor here. And this is going to be what's called a series circuit. And it's series because the current has to flow through everything in series. It can't flow through the battery without flowing through the first resistor. It can't flow through the first resistor without flowing through the second resistor. It literally has to flow through everything, so it's called a series circuit. Okay? So we have one 10 ohm, two 10 ohm resistors, and let's actually change these so they're not both 10 ohms. Let's make one 15 ohms. Okay, so now here's a bunch of questions. What's the current flowing through this resistor? What's the current flowing through this resistor? What's the voltage drop on this resistor? What's the voltage drop on this resistor? Whenever I have something like this, the first place I'm probably going to start is trying to find the current. So let's take a look at drawing this real quick. So when I draw this, I know I've got my battery. Again, no one cares which way you draw it on the Regents exam. So there's my circuit. And on the Regents, they might have something like this. They might have ammeter 1, and maybe they'll put ammeter 2, and maybe they'll put ammeter 3. And then maybe they'll put voltmeters on everything. They're going to measure the voltage across all of this stuff. And we'll call this voltmeter 1, we'll call this voltmeter 2, we'll call this voltmeter 3. And they'll ask like, hey, what's this one going to read? What's this ammeter going to read? What's this ammeter going to read? What's this voltmeter going to read? What's this voltmeter going to read? What's this voltmeter going to read? Well, there's a few simple things, okay? If you go to your reference table, which I'm going to pull up right here, we have a series circuit. Anytime there are things in series, this stuff is true. So for a series circuit, all of the current must be equal. Okay, so let's go back. That means whatever current flows through this must flow through this, must flow through this. So whatever value I find for current has to be the same for all of them. It has to be. That's a series circuit, okay? The voltage says that all of the voltage must add up to the total voltage. Well, what's the total voltage? The total voltage will always be whatever the voltage of the source is. So the voltage of this battery I put as 12 volts. That means V3 must be 12 volts. It has to be because that is the voltage of the battery. Okay, so that is also the total voltage. And then we have this resistance equivalent is equal to R1 plus R2 plus R3. Well, that just means we add up all the resistors to find the total resistance. So how would we solve a problem like this? Well, the first thing we do is, actually, we wouldn't find the current first, we'd find the resistance so we could find the current. So we know that Req, or R total of the whole circuit, is going to be R1 plus R2. We know this is a 10 ohm resistor, and we know this is a 15 ohm resistor. So we've got 10 ohms plus 15 ohms, and now my total resistance is 25 ohms. So to get through this, there is a total of 25 ohms of resistance. All right. Now I want to find the total current. Well, to find total current, I will say the total current is the total voltage divided by the total resistance, or really the equivalent resistance is really the correct way to say it. Well, I know my total voltage is 12 volts. I know my total resistance is 25 ohms. Let's just call it 0.5 amps for now. Okay, close enough. Um, 0.48, fine. 0.48 amps. So there we go. That's a total current. And we know that the total current in a series circuit, because it's on our reference table, is the same everywhere. So that must be 0.48 amps, that must be 0.48 amps, that must be 0.48 amps. Cool. We now know I total equals 0.48 amps. We know Req is equal to 25 ohms. We have two more questions to answer. What's this voltage going to read and what's this voltage going to read? Remember, this is 10 ohms and this is 15 ohms. It in fact is not going to read the same because this is not a parallel circuit, it is a series circuit. So this coulomb of charge, as it moves, has 12 joules of energy it's allowed to give up. If it gave all 12 joules of energy to that resistor, it would have no energy left and it wouldn't be able to keep getting through the circuit. So what it has to do as it goes through the circuit is it has to give a little bit of energy to one resistor and then a little bit of energy to the other resistor. This resistor has a higher resistance, so it's harder to get through. If it's harder to get through, we're going to expect more energy needs to be used to get through it. So let's do the calculations and let's find out. Again, this equation is always true as long as we put our subscripts. V equals IR as long as we put our subscripts. I want to know the voltage through the first resistor, so I'll use the current of the first resistor and the resistance of the first resistor. Well, the voltage across this resistor, the amount of energy that's lost by 1 coulomb of charge on this resistor, the voltage lost, we call it a voltage drop. The voltage drop, because on this side maybe it will have 12 joules, and on this side maybe it'll have 8 joules. I don't know the actual number right now. So on this side, that coulomb has 12 joules, that means it's 12 volts. And if on this side it had 8 joules, it would mean it was 8 volts. So there would be a 4-volt drop across this. Let's find out what the drop actually is. Well, we've got 0.48 amps times 10 ohms. 0.48 times 10 is going to give us 4.8 amp ohms. Well, you can leave it as amp ohms and be 100% correct, or you can change it to 4.8 volts. So I now know this voltmeter will read 4.8 volts. We have two ways to find this voltage then. We know the total has to be 12. So 4.8 plus something must equal 12. Well, let's also do the math out. Let's also do voltage of resistor 2, the voltage drop, how much voltage is lost going through that resistor, with this information. So voltage 2 is going to be 0.48 amps times 15 ohms. Well, we've got our 4.8 plus 2.4, which is going to give us what, people? 7.2. Why did I just say 7.2? Yeah, 7.2 volts. What's 4.8 plus 7.2? It's 12 volts. So it all works out. And let's go check that out. I take my voltmeter and I measure 7.2 and I measure 4.8, and I measure 12. And what do you know? There's something else that's really cool here. The total voltage lost across both of these resistors is 12. And let's just put an ammeter here since we know that current must be the same everywhere. 0.48. I'll put one more just to prove. Okay. There, it's got to be the same everywhere. One more type of circuit. A parallel circuit. And so in a parallel circuit, we have a choice of which way we want to go. And I think I'm going to jump right to a mixed circuit. It's going to be a parallel and a series circuit. I'm going to make it, no, maybe I won't. I'll just do why'd I do that? So wire. We'll do a simple parallel circuit. We'll only put 2 resistors in. Wire, wire. Let's just throw our ammeters in now. It's really important in this parallel circuit if I want to know the resistance, or sorry, the current through this resistor, that the ammeter is part of this resistor, and that the ammeter is part of this resistor. And so if I want to know the current through the entire circuit, I need to make sure that whatever current goes through the battery goes through the ammeter as well. And so the first thing I just want you to notice is, hey, look, this resistor got 0.9 amps and this resistor got 0.9 amps, and they come together and it adds up to 1.8 amps. Now let's change some values. Let's make this 12 volts, 10 ohms, and 10 ohms. We notice that they're going to get the same current, but if one of them has more resistance, it will get a smaller current. So the 10 ohm ends up with more current than the 20 ohm. And let's just go through. How would I solve this if I were going to draw it? Here we go. This will be relatively quick. I've got my battery. I've got a resistor. I've got another resistor. I know that this is 20 ohms, and this is R2, and this is R1, and it's 10 ohms. And what did we make it? Did we make it 12 volts again? I'm sorry, I can't remember. Let's go back and check. I did, I made it 12 volts again. All right, we look at our reference table. Our reference table tells us a few things. One, it tells us that here, if this is ammeter 1 and this is ammeter 2, it tells us that I total is I1 plus I2 plus however many different paths there are. So it tells us that for a parallel circuit, all of the current has to add together. It tells us that the voltage has to be the same in each branch. And that makes sense because if I'm a Coulomb and I decide to go right or I decide to go this way, I'm going to carry the same amount of energy. To get from this side to this side, I have 12 joules of energy if I'm a Coulomb. And I give up that 12 joules of energy either to this resistor or to this resistor. So either way, those resistors get to have all of the energy. And the only other thing I have to find is I have to find REQ. And REQ looks like this on my reference table. What's really important, oh, you can't see that. What's really important, and the mistake that's made very often, is that it's 1 over R1 plus 1 over R2, and it's 1 over REQ. It does not say this. A lot of students just do this. They do 1 over plus 1 over, and they're like, there you go, that's the resistance. No. There's a 1 over everything, so let's see how we solve this. Let's start by finding the total resistance of the entire thing. That's what we're going to do first, because that's what I feel like doing. 1 over REQ will equal 1 over 10 ohms plus 1 over 20 ohms. That is not 1 over 30 ohms. That is not 2 over 30 ohms. I have to find common denominators, okay? If I'm going to find common denominators, look at that, my hair's all messed up. If I'm going to find common denominators, I got to look at these and I go, okay, what's the most common thing I could have? And it's going to be 20. So this 1 over 10, I will change to 2 over 20 ohms plus 1 over 20 ohms equals 1 over Req. Now I can add them. So now I've got 1 over Req equals 3 over 20 ohms. And the next thing I'm going to do is I'm going to flip everything over because that 1 over Req is not the answer. I have to flip it. So Req will equal 20 ohms over 3. All right. So the total resistance in this circuit is going to be 6.6. Flipping out. So Req, where can I write this already here? 6.67 ohms. What that means is I could effectively have the exact same thing with a single resistor that was 6.67 ohms. These are equivalent circuits is what that means. So if I want to know now the total voltage going through, I use the total current going through. I total will be V total over R total, but really that R total is Req. So now I've got 12 volts divided by 6.67 ohms. Plug that in a calculator. 1 point, we'll call it 1.8, 1.8 amps. Let's go check it. What do you know? 1.8 amps. What if I wanted to know the current through either one of these? I'm not going to do both. I don't have to do both to show how this works. Again, I just pick which one I want to know the current for. Maybe I want to know the current for this resistor. I will use the voltage on that resistor and the resistance of that resistor. And the voltage on both of these must be 12 volts. They both get all 12 volts. So 12 volts divided by 20 ohms is I2. So 0.6 amps for I2. And we know that's right already. 0.6 amps. I think that's it for today.